Next, we can finally address addition of vectors. Let's work again in the first quadrant, and then everything we do can then be generalized to the entire plane. Let's say that we have two vectors, A and B, and we want to add these two vectors. We'll do it in the usual way. First of all, we move the vectors so that they're head to tail, as before. We connect them and draw the resultant vector, which we call C. Now we ask the following question. How are the components of C related to the components of A and B? And you'll see in a second why we ask this question. We can do this in the following way. First of all, we draw the components of A as usual. Secondly, B is not at the origin, but because the XY frame is just a fictitious frame that we use to orient ourselves on the plane, we can draw an additional XY frame at the origin of B, and then draw the components of B at that location. Then we're almost done. We slide AY to align with BY, and BX to align with AX. And notice that now we have a right angle triangle with hypotenuse C and two sides given by the components of A and B. We can draw the components of C now, and we see that there are those two green lines there. And therefore, we can infer from this that the components of C are nothing but the addition of the other two components. That is, Cx is equal to AX plus BX, and Cy is equal to AY plus BY. So this tells us that if we want to find the components of a resultant vector, all we have to do is find the components of the individual vectors that we're adding first, and then add those component-wise. Once we know the components, we can clearly find the magnitude and direction of the vector C by using the Pythagorean theorem and the inverse tangent function. This procedure is known as the addition rule for vectors. We have done it for two vectors in the first quadrant, but it's completely general. It applies, of course, to any quadrant, and it also applies to any number of vectors. What's really important here is that you have to understand that what we're doing is adding the components, not the magnitudes. So when you want to find the magnitude of C, you should never add the magnitudes of A and B as in the equation above there. That equation is always wrong and should never be used. I think we're ready for an example. So let's look at how we put all of this together. Let's say that in training for a 10K race, you run along the following paths. You run along A first, which is 5.25 kilometers at an angle of 35 degrees, and B, which is 4.75 kilometers at an angle of 95 degrees. Both vectors are in standard form, so the angles are taken to be with respect to the positive x-axis. And notice that the two lengths, when added, give you 10. So the sum of the magnitudes of A and B is 10 Ks because that's what you're training for. We want, first of all, to sketch the two vectors and their sum in the xy plane. We then want to calculate the distance from the initial to the final location. That is, we want to calculate the magnitude of the resultant vector C and the angle it makes with the positive x-axis. Let's start by drawing the vector. As always, we draw an xy plane, and then we draw the two vectors. Let's say we draw the first vector here, A. This is about 35 degrees, more or less. We're just sketching them, so it's not very important. And then B, because it's 95, it's a little more than vertical, so it's something like this. And it's a little shorter in length than the vector A. The resultant vector C is going to be the sum of the two, which means it's going to be the vector that goes from the tail of A to the tip of B. Therefore, C is given by A plus B, like that. We now want to find the magnitude and the angle that this vector makes with the positive x-axis. So we proceed as usual. We find the components of the two vectors. Ax is given as usual by the magnitude of A times the cosine of the angle that A makes with the positive x-axis, which is 35 degrees. This would be a good moment for you to stop the video, attempt this example yourself, and then look at the solution. I'm assuming that you're going to do that, so I'm just telling you the answer. The x component of A is going to be 4.3 kilometers. Likewise, the y component of A is given by A times the sine of 35, which is 3.01. For B, we do exactly the same thing. So I'm just going to write down the answers because it will be B times the cosine of the angle for the x component and B times the sine of the angle for the y component. We get negative 0.41 kilometers and 4.73. Now to find C, x, we add ax plus bx, and that gives us 3.89. And cy is the sum of the two numbers above there, which is 7.74 kilometers. Now we have the two components. We want to find the magnitude, and we do that by using the Pythagorean theorem. So this is the reason why we want to find the components of the vector c, because the only way to find the magnitude is to find the components first. Once we plug in the numbers here, the two numbers that we just obtained, we get 8.66 kilometers. So notice right away that the magnitude of c obeys this inequality here. As I said, c is not equal to the magnitude of A plus the magnitude of B. It's actually less. This, in case you're interested, is known as the triangle inequality. For the angle, we take the inverse tangent of the y component over the x component. And again, make sure your calculator is in degrees and not radians. And the answer you get is 63.3 degrees. And we've solved the problem. That's all there is about addition of vectors. Once again, I hope you guys found this video useful. Please like, share, subscribe, and make sure you hit the notification button.